Thank you very much. So yeah, this is a work on classification with unknown class-conditional label noise on non-compact feature spaces, and it's a joint work with Attica. So the setting is classification with label noise. So we have some probability distribution over triples, x, y, and noisy y tilde. So x is some feature vector in a metric space, y is some true binary label, and y tilde is some noisy label which may or may not be equal to our true label. And the goal is to find a classifier phi which, given a feature vector x, outputs the true label, and we quantify that in terms of the usual risk or error rate. And the learner is given access to a corrupted sample consisting of ordered pairs with a feature vector x and a noisy label y tilde. And the difficulty comes from the fact that you only have access to this corrupted sample and you don't have any access to the true labels. So we need to make some assumptions about the relationship between the true labels and the noisy labels, and in this work we're going to make the assumption of unknown class-conditional label noise. So there are some unknown label noise probabilities, pi 0 and pi 1, and pi 0 gives the probability that if the true label is 0, the noisy label is 1, and pi 1 gives the probability that if the true label is 1, the noisy label is 0. And this problem becomes challenging whenever pi 0 is not equal to pi 1. And essentially this is because it creates a shift in the decision boundary between the noisy labels and the true labels. So the key kind of motivating questions in this area are, can we learn a consistent classifier from data with unknown label noise? And if so, what are the optimal finite sample rates? And finally, how do these finite sample rates compare with the optimal rates for learning without label noise? So the classic work in this setting is due to Blanchard, Lee, and Scott, and he showed that under the range assumption, you can learn consistently with unknown label noise. And the range assumption essentially says that the infimum of the regression function over your feature space is 0, and the supremum of your regression function over your feature space is 1. And under this strong assumption, you can get a consistent estimator for the label noise probabilities, and this means you can consistently learn with unknown label noise. Moreover, on the negative side, he proved a lower bound which shows that without further assumptions, you cannot get any finite sample rates. So the first finite sample rates were derived by Scott, and he showed that if you make a stronger assumption that there is part of your feature space where the regression function is uniformly equal to 1, and there's part of a feature space where the regression function is uniformly equal to 0, you can learn at the optimal parametric rate. So we make it basically, Scott makes this very strong assumption that there's part of the feature space of positive measure where the regression function is uniformly equal to 1 and uniformly equal to 0. And more recently, in the non-parametric setting, under the assumption that we have a uniform lower bound on the density, we've shown that we can also obtain the minimax optimal rate for learning in the non-parametric setting. So in all previous settings, we basically have some very strong assumptions on where we have the extrema of the regression function. And under these strong assumptions, we basically get back the same minimax optimal rates up to logarithmic factors as we had in the setting without label noise. And so kind of a key question for us is, if we make less restrictive assumptions, are there settings where we can obtain finite sample rates? However, we learn at a strictly slower rate necessarily than the optimal rate for learning without label noise. So with this motivation in mind, we move to the non-compact setting. So in this non-compact setting, we're just assuming that we have some smooth regression function, but we don't have any uniform lower bound on the density function. And moreover, the regression function may approach its extrema asymptotically in the tails of the distribution. So this is somehow the natural setup in the non-compact setting. And this builds on prior work in the non-compact setting due to Gadat, Klein, and Marteau, and Cannings and Samworth. So to be more precise, we're making the following assumptions. So if mu is the marginal distribution over the feature space, we're going to assume that there exists some density, which we're going to denote by omega. And the first assumption, which is very mild, just says that the measure of a metric ball of radius r is roughly equal to the density times r to the d. And in addition, we make a tail assumption. So it just says that if you look at the set of points in the tail where the density is strictly less than epsilon, that's upper bounded by some constant times epsilon to the gamma. So this in particular is much, much more mild than assuming a uniform lower bound on the density, and it holds for lots of natural distributions, such as the Laplace distribution, Gaussian distribution, and mixtures thereof. Okay, so in addition, we want to make some more standard classification assumptions. So we're going to make the classical Chebyshev margin assumption, and we also make the standard Holder assumption on the regression function. So with these assumptions in play, Gadat et al. Had already arrived the optimal minimax rate for learning from clean labels. So here you can see that this depends kind of, without passing the details of the rate, it depends upon the smoothness, the Holder exponent, the dimension of the feature space, and crucially, it depends upon the tail of the distribution. So that gamma parameter is how quickly you're decaying in the tail of the distribution. And we're working in the setting of classification with unknown label noise, so we need to make one additional assumption, and this is kind of a quantitative range assumption, which is still strictly weaker than Scott's assumption. So essentially, we're going to assume that if we look at the set of points, this bounded region of the space where the density is bigger than epsilon, then the infimum over that set is no bigger than a constant times epsilon to the tau, and the supremum over that set is at least 1 minus a constant times epsilon to the tau. So to emphasize, this is strictly weaker than both Scott's assumption and the assumption of a uniform lower bound on the density with the range assumption. So to visualize this assumption, basically, if tau is very large, we're approaching the extrema very quickly, so we have something like the red line. If tau is much smaller, then we have something like the blue line, where we're approaching the extrema of our regression function much more gradually. So in this setting, the main result is as follows. So we characterize the minimax optimal rates for learning with corrupted data with unknown label noise. So if tau is sufficiently large, then you get back the same rate as Gadat et al. For learning from clean labels. However, if tau is smaller and you approach your extrema much more gradually in the tails of the distribution, then you get a different rate. So this is kind of the first situation where you have finite sample rates for learning with unknown label noise, yet we know that they necessarily differ up to more than logarithmic factors. Okay, so just to summarize, we've determined the minimax rates for classification on non-compact domains with unknown class-conditional label noise, and these rates display some interesting threshold behavior which is unseen in the noise-free setting, and in particular it depends upon the behavior of the regression function in the tails of the distribution. And moreover, to obtain the upper bound in these rates, we constructed a classifier which is locally adaptive to both the unknown density and the other distributional parameters. So all it needs to see is this corrupted sample, and we have attained a high probability performance bound for this algorithm, which is minimax optimal up to logarithmic factors. So yeah, thank you very much for listening.